So far, we have only worked with very, very simple systems. But you can imagine that if we have lots of springs, dampers, and masses all connected together, like this slinky where I've connected the three of the sections together, then we might end up with an ordinary differential equation that has a separate equation for every state, and things might get a bit complicated. That is where vector and matrix representations become really useful. You should think of these as largely being useful notation. That is, vector representations and matrix representations of ordinary differential equations primarily serve as a way of organizing information in a nice, convenient way that helps with computations. Let's say that we have a linear, constant coefficient first-order differential equation that has states x, y, and z. We have x dot equals x plus 2y plus 3z. Y dot is equal to y plus 4z, and z dot is equal to x plus z. I've spaced these numbers and letters in a way that will help us in a moment. You can imagine that if I had 50 or 100 or even 1,000 states here, this could become very challenging to manage. I'm going to group the states together in a single vector, x, y, z. And by definition, the time derivative of this vector of states is equal to the vector of time derivatives of the states. That is, d dt of that vector is equal to the vector x dot, y dot, and z dot. So far, I haven't done anything very interesting. I'm just putting variables into a list. Now comes the useful part. I'm going to define a matrix to be an array of numbers, like A equals 1, 2, 3, 4, 5, 6, 7, 8, 9. This is a matrix that has 3 rows and 3 columns with a total of 9 numbers. Our goal is to define some notion of multiplication between the matrix A and the vector of states, so that if I take A times that vector of states, I will get the right-hand side of the differential equation. In fact, if I relabel W as x, y, z, then I can actually use the notation AW is equal to A times x, y, and z. The right way to define multiplication between A and W is to take elements of the rows of A and multiply them by their corresponding elements of the state vector and sum those together. For instance, if I take the A matrix I just defined, A times W is equal to the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9 times the vector x, y, z, and that's equal to 1 times x plus 2 times y plus 3 times z. And then the second row is 4 times x plus 5 times y plus 6 times z. And then the last row is 7 times x plus 8 times y plus 9 times z. Note that the result is a vector again, so multiplying a matrix times a vector gives a vector. Now let's go back to the differential equation and see how we could choose different values in the components of A so that we get the right-hand side of the differential equation we started with. The idea is to choose the elements of A so that when you multiply A and the state vector, you get the right-hand side of the differential equation. If you look at how I wrote the differential equation, I want you to focus on these columns that I'm circling in yellow. It's reasonably easy to figure out what A should be. In particular, if I choose A to have the columns that I just put rectangles around, I can have A be equal to 1, 0, 1, 2, 1, 0, 3, 4, 1. And if I multiply that by the vector x, y, and z, I get 1 times x plus 2 times y plus 3 times z, and I get 1 times y plus 4 times z in the second column, and I get 1 times x plus 1 times z in the third row. This has important consequences because now I can rewrite the differential equation as w dot is equal to AW. This is exactly the same equation as the one I started with, but with a different notation being used. Now, how is this useful? Let's think back to lecture 4. I'd like to use this vector and matrix notation in my Euler integration code. The initial condition for the differential equation needs to include initial conditions for all the states. So I'll define W0 is equal to the vector x0, y0, z0. An Euler integration expressed in terms of vectors and matrices will look like w of t plus dt is approximately equal to w at time t plus dt all times a times w at time t. The great thing about this formula is that once you have the matrix A, the code for your Euler integration will always look the same. As an example, let's look at the vector and matrix notation for a spring mass system. Here we have a wall, we have a spring, and a mass. We know from lecture 7 that we get a second order differential equation. X double dot is equal to minus k over m times x. And we can rewrite that in first order notation as x dot is equal to v, and v dot is equal to minus k over m x. Now, if we set w is equal to the vector x, v, and if we set A is equal to the matrix 0, 1, and then minus k over m, 0, we get A times w that gives us the right-hand side of the differential equation. Now let's say that x0 is equal to 0.5 and v0 is equal to 0. This means that w0 is equal to the vector 0.5 and 0. We want to use this vector notation in Euler integration with a time step of dt is equal to 0.1. What should that look like? We set w0 to be the vector of initial conditions of the two states, and then we find that w of 0.1 is approximately equal to w at time 0, which is 0.5 and 0, plus dt, which is 0.1, times a, which is 0, 1, minus k over m, 0, all times w at time 0, which is, again, 0.5 and 0. The idea here is that if I multiply this out, then I'll get the update of a w at time 0.1. Just as in lecture 4, we can repeat this process as many times as we like to get an approximate solution of the differential equation at any time. What should you remember from today? Vector and matrix representations are really, really useful for organizing information. The more complex a system is, the more useful this notation becomes. If you find yourself using vector and matrix notation a lot, and as engineers we use them all the time, you will eventually take a class that focuses on them. But for now, just think of them as the notational convenience that simplifies your life.